So today we're going to continue our unit on bonding and talk about bond energy. So first let's kind of finish up our conversation about ionic compounds. Percent ionic character is the measured dipole moment of the bond divided by the calculated dipole moment of those plus and minus ions put together times 100%. So ionic character will increase with electronegativity difference. So the larger the difference, the more ionic character. No bond can ever reach 100% ionic character. And so what this means is that no bonds are completely ionic. So there's a couple of reasons for this. The first is that results are in the gas phase, not solid, and so that lends to them not being completely ionic. Also, many compounds contain polyatomics, which, if you remember, polyatomics are basically covalently bonded. So they're held together by covalent bonds, and then they're an ion that then join with usually a cation or sometimes an anion to form an ionic compound. And so we've got some covalent bonds going on there. So any compound that conducts an electric current when melted is also classified as ionic. And remember, it can also be dissociated in water and conduct electricity as well. Okay, so now let's talk about the covalent bonds. Let's do a little bit of review. A chemical bond is a force or forces that cause a group of atoms to behave as a unit, basically sticks them together. Bonds result from the tendency of a system to seek its lowest possible energy. So if you remember, a lot of the conversations we've had have been about finding either the electron configuration or the bonding orientation that will give the lowest possible energy. So if we take a look at methane, which is CH4, its heat of formation is 1,652 kilojoules per mole. So for each C to H bond, if we take a look at CH4, we've got a carbon and then 4 hydrogens bonded around that carbon. So for each of these bonds, so for example, this hydrogen to this carbon, it's that total heat of formation divided by 4, and so each one is 413 kilojoules per mole. If we look at CH3Cl, the heat of formation is 1,578 kilojoules per mole, and we assume that all C to H bonds represent the same quantity or the same amount of energy, and so since we already calculated the C to H bond in the methane, then we assume it's going to be the same, and so we take our total minus 3 times the C to H bond energy, and this gives us the C to Cl bond energy. Now, this whole bond concept is a human invention, but we're using it to figure out the amount of energy contained within a compound. Okay, so we know that molecules are collections of fundamental components, or bonds. And we know that sharing electrons gives a lower energy state because they are simultaneously being attracted by 2 nuclei. So the electrons are being pulled by 2 nuclei. That's going to be a lower energy state. Chemical bonds, like we said, are only a model to show this. Okay, so let's relate this to some covalent bonds. Okay, so when we take that methane, that CH4, and break it into 4 bonds, each C to H bond is going to require a different amount of energy. And so we can take an average, and then we apply that average to all C to H bonds in all molecules, and that's how we got that, I believe it was 413 in the previous example. Okay, we're taking an average. So bond energy is going to depend on the environment. And there's an appendix in your book that gives you bond energies for several different bonds, C to H, O to H, some double bonds, triple bonds, whatever. Okay, let's talk about the 3 main types of bonds. So we can have a single bond, which is 1 pair of electrons being shared, and we usually draw 1 line to show that. We can have a double bond where we have 2 pairs of electrons being shared, and so we have 2 lines. And then we can also have a triple bond, and this is where we have 3 lines or 3 pairs of electrons being shared. Okay, so let's relate this bond energy in enthalpy. So bond energy values can be used to calculate the approximate energy for a reaction, heat of formation. So we have hydrogen plus fluorine producing hydrofluoric acid. To break bonds, we have to add energy to the system. This is an endothermic process to break the bonds. When we form bonds, energy is being released. This is an exothermic process. So when we break up our hydrogen and our fluorine, those are going to be endothermic. When we form hydrofluoric acid, that's exothermic. Delta H is the sum of the energies required to break the old bonds plus the sum of the energies released in the formation of the new bonds. So we're basically calculating the overall energy for that process. What is the delta H? So the equation is delta H is equal to sum of D for bonds broken minus the sum of D for bonds formed. And D represents the bond energy per mole of bonds. So it's bonds that are broken, so this would involve reactants, minus the sum of all the energy for basically bonds that are formed, which would be products. So for our hydrofluoric acid, delta H is equal to the bond energy of the H to H bond plus the bond energy of the F to F bond, and I guess I would kind of group those together, minus 2 times the energy of the H to F bond, because if you notice from our reaction, we have 2 hydrofluoric acids, and so that's why this 2 is here. Okay, so we can look up these values in a chart. So it's 1 mole from the H2, whoops, I keep hitting that button, times the H to H bond energy plus, and I would actually group these together like that, 1 mole times the F to F energy minus 2 times our H to F bond energy. And remember the 2 coming from the balanced chemical equation. And so if we put all those together, we get an overall answer of negative 544 kilojoules. So let's take a look at an example. Okay, so we want to calculate the bond energy for this reaction. So remember, we're doing reactants to products. If we look at CH4, we have carbon, hydrogen, 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 hydrogen. So I know we have 4 C to H bonds. C to H, and we're going to do 4 of them. So 4 times the C to H bond plus Cl2 is Cl to Cl. So I'm going to have 2 times a chlorine to fluorine bond plus 2, and then fluorine is the same because they are in the same group. They're going to bond similarly. So these are all my reactants minus, I have CF2Cl2, so 2 fluorines, 2 chlorines. So I have 2 C to Cl bonds and 2 C to F bonds. Ooh, before we go any further, and this has already been done, but it's always good to check, make sure your equation is balanced before you move on any further. Okay, so now I've got 2 H to F, so this is just H to F, and then 2 H to Cl bonds. And so now we need to look all these values up in a chart. Already done that for you. So C to H is 413. This is kilojoules per mole. And since this is the number of moles, our moles will cancel, leaving us with kilojoules. 2 times our Cl to Cl is 239. F to F is 154. All of that minus 2 times C to Cl, which is 339, plus 2 times C to F, which is 485, plus 2 times H to F, which is 565 kilojoules per mole, and then 2 times H to Cl, which is 427 kilojoules per mole. So remember that D is always positive. This is where we're doing our endothermic to exothermic. So if we put all of that together, that gives us negative 1,194 kilojoules. So this overall is an exothermic process. Okay, let's relate this to the localized electron model. So a molecule is composed of atoms that are bound together by sharing pairs of electrons using the atomic orbitals of the bound atoms. Those bound electrons are what's going to determine sharing, bonding, etc. Okay, lone pairs are pairs of atoms that are localized on an atom. So if we take a look at, let's see, water is a good one. So we have hydrogen, oxygen, hydrogen, and then oxygen has 2 what we call lone pairs. So they're localized on that atom. Bonding pairs are pairs that are found in space between the atoms. So we drew a line here to represent a single bond, but this would be a bonded pair, and this would be a bonded pair, and they are shared between the oxygen and the hydrogen. Okay, there are three parts of this localized electron model. The first is that the description of the valence electron arrangement in the molecule, we use Lewis structures in order to do that arrangement. We will talk about Lewis structures. Prediction of the geometry of the molecule is through VSEPR, which represents valence shell electron pair repulsion. So again, next time we're going to talk about Lewis structures, VSEPR. And a description of the type of atomic orbitals used by the atoms to share electrons or hold lone pairs. And so we can take Lewis structure and VSEPR and come up with different geometries. And so that's what we'll be doing next time.